Hi, in this video, we want to talk about blocking in experimental design. Okay, so we're in the situation that we are setting up our game plan for collecting our data. So it is key to understand in this video that what we're talking about is before I have collected any data. Now, I may have done like preliminary research. I may have, taken data from other studies, but this is for when I'm going to be doing hard and heavy data collection, and I want to make sure I get the most bang for my buck, the most output from my effort from my data. And so blocking is what we're going to do when I know that there's a variable that's important, but I'm not interested in it. I'm interested in some other variable. And so, we're going to present just the most simplest, presentation of blocking in this video, and hopefully that it becomes clear what you would do for, more, nuisance variables. All right, so in experimental design, blocking is a technique to reduce the influence of confounding variables. And so the goal of our experiment is to study a certain aspect, a certain treatment on the response variable. However, like if I already know that another variable has impact on my target variable, I know it, I don't need to study it. The influence from that variable is not interesting, it's a confounding variable. So it's often the case that certain uncontrollable nuisance variables can influence the response. We're not interested in these, but we know that they're there. These nuisance variables can create noise and making it difficult to see the signal, the effect of the treatments that we're actually interested in. And that's where blocking comes in to save the day. Blocking in experimental design is for controlling the influence of nuisance variable by creating homogeneous groups or blocks across which the nuisance effect is assumed to be like constant. By doing so, we're able to isolate and reduce the effects of these nuisance variables on the response variables, thereby making the effect of the treatments of interest more apparent. In essence, blocking is an experimental design for stratification, or is blocking is to experimental design, what stratification is to observational studies. All right, so mathematically, we're going to represent the blocked experiment mathematical model as the response is equal to an overall average plus the impact of the treatment that we're interested in, plus the impact of our nuisance variable, plus an error term. And the error term accounts for all aspects of the situation that our data and our model can't account for. All right, so let's talk about nuisance variables. And so a lot of times they're not controllable, sometimes they are. What we want to do, we want to make sure that we kind of like even out our nuisance variable among our different groups so that we don't have an impact from those manifesting mathematically. So in experimental design, we will encounter variables that are not of primary interest, but we know that they have an impact on our target variable. And so these are called nuisance variables. And usually there's factors, but they could be like numeric, you know, and these typically are things that we cannot control or manipulate in the course of an experiment. And so we use the term uncontrollable nuisance variables. Nuisance variables pose a significant challenge in experimental design as they can introduce additional variability into results and potentially obscure the effects of the treatment of interest. In statistical terms, they contribute to the error term, thereby increasing the variability of the response. Examples of nuisance variables could be environmental conditions such as agricultural experiment, where we have temperature, humidity, or wind speed. In a clinical trial, a nuisance variable might be age, gender, or underlying health conditions of the participants. And so it's important to note that nuisance variables aren't bad. They're just simply variables are not the focus of our experiment, and we're really not interested in them, even though we know that they're important. However, their presence can interfere with our ability to detect the treatment effect that we're actually interested in. To deal with nuisance variables, one approach is to use randomization. By randomly assigning treatments to experimental groups, we can, on average, balance out the effects of the nuisance variables across the treatment groups. However, it can work out that the averaging out doesn't kick in. Maybe we don't have enough data. Maybe we don't distribute things correctly through the randomization. We might just get like a random number generator that doesn't really do the distribution of things as well as we would like to. So if we a priori, before things happen, if we suspect that there's a nuisance variable that will have a large effect on our outcome, a better approach will be to use blocking. The idea behind blocking is to first group the experimental units into groups, such that the units within groups are as similar as possible with respect to the nuisance variables. And so by doing this, we minimize the variability within blocks and hence reduce the impact on the treatment effects. We can then compare the effects to different treatment groups within each block, which allows us to isolate the treatment effect more effectively. So what we would be doing here, let's say that I've got 2 treatment groups. I would want to have in each group equal proportion of females, equal proportion of males, if gender or sex is believed to be related to the target variable. We want to have everything, we want our groups to be as even as possible with respect to all of our nuisance variables. Now let's compare randomization to block experimental designs. So randomization and blocking are 2 fundamental techniques for controlling the influence of nuisance variables and for minimizing bias in our experiments. However, they serve slightly different purposes and are best used under different circumstances. Randomization is a process of randomly assigning the experimental units to different treatment groups. It serves 2 primary purposes: balancing the effects of the nuisance variables and a basis for inference. By randomly assigning treatments, we ensure that on average, the effects of nuisance variables are evenly spread out across groups. This helps to reduce the potential bias in estimating the treatment effects. Now, the randomization process provides a theoretical basis for statistical inference. It ensures that the observed differences in the response variables between the treatment groups are solely due to treatments themselves, not to systematic biases in the way that the experiment was conducted. Randomization is a powerful tool, but its effectiveness in controlling nuisance variables relies heavily on the size of the experiment. And here is its shortcoming. In small size experiments, there is a non-negligible chance that the randomization might fail to balance things out, which can obscure the treatment effects. Now, blocking, on the other hand, is a technique used to reduce the variability of the response variable by grouping similar experimental units together into blocks. The idea here is to isolate the variability due to the nuisance variables, thereby enhancing the precision in estimating the treatment effects. By making comparisons within groups where the nuisance variables are controlled, we can more clearly see the impact of what we're actually interested in studying. Blocking is particularly useful when, 1, we can easily and clearly identify the nuisance variables that could have a significant impact on the situation, or 2, the experimental size is relatively small, making it difficult for randomization alone to balance out the nuisance effects. So randomization is better for larger data sets, and it's better when I honestly don't know what the influential variables are that could be causing a problem. Blocking is better when I can clearly identify nuisance variables and when I have a smaller data set. So randomization spreads the effects of nuisance variables evenly across treatment groups, which helps to ensure the observed effects are due to the treatments themselves, but requires more data. Blocking creates similar groups for our treatment levels and increases the precision of the treatment effect estimates. Ideally, in a well-designed experiment, we would actually use both randomization and blocking to control nuisance variables. We would first block the experimental units to control the known and significant variables, and then randomly randomize the treatments within each group to handle any remaining unknown or uncontrollable nuisance variables. All right, now to implement blocking in R, what we're going to do, I'm going to have some dummy data with this. So something that's important to remember in experimental design, all of this is before I collect data. When I go and I grab data in R, it already has the data. So we have to pretend, close your eyes, pretend that the response variable is not known. And what I'm doing is setting up what's going to happen down the road. So let's go ahead and take the tooth growth data set in R. And so this is on, the growth of guinea pig teeth. This data set has a blocking structure, and we have two supplementary delivery methods. We have OJ and BC applied at different dosage levels. So what's of interest is actually the dosage level, not the delivery method. And so what we want to do, we want to make sure that we have things blocked out. And so in our data set, we have lin, which is the length of the teeth, our target variable, the supplemental that is given, and then the dose given. All right, so we're interested in the effects of the supplemental and the dosage on tooth length. The supplemental variable, this is actually an error. The supplement is a nuisance for us. We are interested in the dose itself. And so here I can just run a model and I can get what I've got. And so in this situation, the scenario we're presenting is that we would be doing, we would be doing random assignment of which supplement and which dose they get. And if there was like gender in here, we would want to have gender even for the different groups. All right, so now for interpreting the output of blocking, it's going to be just like ANOVA. I mean, almost always it's going to be very similar to ANOVA. We could do something more advanced with linear regression or other types of models. But typically when we talk about blocking, we're talking about ANOVA. And so it's going to run the same way it went before. We'll have our degrees of freedom, our sum of squares, our mean squares, F statistic, and the p-value. And we're going to always check to see, is there a significant interaction first when I interpret? So first thing I want to check is significant interaction between treatment and blocks. Is there a significant effect on just the blocking by itself? And after that, then I'm going to actually look at the treatment itself. Treatment is actually the last one I'm going to look at as I interpret. And the reason for that is that if there's no interaction, I'll consider running my analysis without the interaction on there, with just the blocks. If after that blocking is not statistically significant, then I potentially remove that noise from the study and just focus and rerun the model with just the treatment by itself. When is it most beneficial to apply blocking? And so blocking is an effective strategy for controlling variability due to extraneous or nuisance variables that are known and uncontrollable. Blocking helps increase the precision of experiment and improves the efficiency of statistical analysis. However, the choice to use blocking in experimental design depends on various factors. So if I have a large impact from a nuisance variable, I want to use blocking. If my nuisance variables are known and measurable, I want to use blocking. We have limited experimental resources, I want to use blocking. If I have tons and tons of experimental resources, I could just do things over and over and over with randomization and get my results, and randomization will do a pretty good job, but it takes a lot of iterations for us to be able to get that convergence aspect going. Now, blocking is best when we have homogeneity within groups or within blocks. And we want to have the ability to apply all treatments in all blocks, which may not be the case of a particular study. So in conclusion, blocking is a valuable technique used to control for nuisance variables that we could otherwise confound our treatment effects. By grouping together similar experimental units into blocks, we can minimize the variability within blocks, allowing for clearer comparisons between treatments. This, in turn, improves the precision of our experimental results and enables us to make more accurate inferences about the effects of the treatments. We've seen how implementing blocking in R using the LM function for linear models and the ANOVA function for the analysis of variance. By examining the ANOVA table, we can determine whether our blocking was effective, whether the treatment had a significant effect, and whether the treatment effect carries across blocks. However, the decision to use blocking in experimental design should be made judiciously. It is important to know when it's most beneficial to tackle nuisance variables with blocking. And so that's going to be when the nuisance variables are known and measurable. Nuisance variables have a large impact on the response variable, and when there's homogeneity within the blocks. Blocking is also useful in small size experiments when randomization alone isn't going to be enough for balancing out the effect. A well-designed experiment often employs both randomization and blocking as complementary strategies to control the nuisance variables, with randomization used to deal with unknown or uncontrollable nuisance variables, and blocking is used to deal with the known nuisance variables. By adopting these strategies, we can ensure that our experimental results are valid and reliable, and our conclusions are founded on solid statistical evidence. All right, here are the homework problems I've got for you. And that's all I've got. Life is short, do math.